Hi everyone, welcome to WinPoint online classes. In this session, we are going to start a new chapter. The name of chapter is Magnetic Effects of Electric Current. Let's start the discussion. In the previous chapter on electricity, we learned about heating effects of electric current, light effect of electric current. In this chapter, we are going to learn the magnetic effect of electric current. We all are familiar with magnet, right? Magnets are having two poles, north pole and south pole. And you might be knowing about the interaction between the poles. North pole and north pole will repulse each other. North pole and south pole will attract each other. Means unlike poles attract each other, like poles repulse each other, right? Magnetic force is a non-contact force. There are two types of forces, contact force and non-contact force. The force acting with contact, it is known as contact force. Friction is a contact force, muscular force is a contact force. But there are some forces which are acting without contact. These forces are known as non-contact force. Magnetic force is a non-contact force. In this chapter, we are going to learn about magnetic force. The topic which we are going to cover in this session are magnetic field lines, current carrying conductor, magnetic field intensity, right hand thumb rule. This topic we are going to cover in this session. First one, magnetic field. We are going to learn about magnetic field. For that, we are going to consider a magnet here. It is a magnet. And for this magnet, there are two poles, north and south pole. The white dot is indicating north pole and other pole is south pole. The white dot is indicating north pole. And we are going to place some of the nails around this magnet. Here you can see a lot of nails now. These nails are made of iron. We know that iron and magnet, there is a force of attraction between iron and magnet because iron is a magnetic material. These all iron nails are going to get attracted by this magnet. So what is going to happen? Let's see that. All nails are attracting towards the magnet. These nails are moving towards magnet, right? This nail is not moving. What would be the reason? The nail is outside of the magnetic field. This magnet is having a field around it. If the nail is inside that field, then only there will be force of attraction. Outside the field, there is no force of attraction. So here, there is a region around the magnet. That region is known as magnetic field. In this region, we can feel the presence of magnet. In this region, we can feel the presence of magnet. This region is known as magnetic field. Here, we are going to place a nail here. Is there any attraction between this nail and magnet? No, because it is outside the field. But when we are moving this nail to inside the field, now what is going to happen? Now this nail is going to get attracted by the magnet. This is the concept. It's very simple. Around the magnet there will be a field. That field is known as magnetic field. In this field we can feel the presence of magnet. Now let's write the notes. Magnetic field. Magnetic field, it is a region around a magnet in which the presence of magnet can be felt. Next one. Now we can discuss magnetic field lines. Magnetic field lines, is there any line around the magnet? There are some imaginary line around the magnet. We are going to discuss that. For that, we are considering a magnet. It is a magnet. This pole is north pole, this pole is south pole. There are some imaginary line which is starting from north pole. These are loops actually, these are circular loops. But it is going from north pole and it is going to south pole. These imaginary lines are known as magnetic field lines. We are going to draw the magnetic field line here. Here you can see that magnetic field line, the direction is from north pole to south pole. Here you can see the direction. It is starting from north pole and it is ending at south pole. These are magnetic field line. These are imaginary line which is starting from the north pole, ending in south pole, ending at south pole. Now let's write the definition for this magnetic field line. Magnetic field lines, the imaginary lines starting from north pole and ending at south pole of a magnet. These lines are known as magnetic field line. It is starting from north pole and it is ending at south pole. Actually, it is not starting, it is not ending. It is a circular loop, continuous loop, but it is going from north pole and it is going to south pole. That's the concept. Next topic, magnetic field intensity. What do you mean by the term intensity? Intensity means the power. the magnetic power, magnetic field intensity, magnetic power. Let's consider a magnet and these are the magnetic field line around it. Can you guess in which area magnet is having more strength? Yes, here, near to the pole, north pole and south pole. The magnetic field intensity is more in this area because the field lines are very close to each other. Here you can see that the field lines are very close to each other. At this region, the strength is more. So what is magnetic field intensity? It is a degree of closeness of this line. If the lines are very close to each other, then the magnetic field strength is more. The magnetic field intensity is more. So we can write that magnetic field intensity depends on degree of closeness of magnetic field line. So magnetic field line, how much close it is? If it is too much close, if the magnetic field lines are very close to each other, the intensity will be more. Magnetic field due to current carrying conductor. Current carrying conductor and magnetic field. Is it possible? Yes. If current is passing through a conductor, there will be production of magnetic field. Without magnetic field, there is no current flow. If there is a current flow, there will be production of magnetic field. They are brothers, right? Magnetic field and electric field, they are brothers. Here you can see a circuit. There is a battery here. There is a conductor. It's a conductor. Conductor means it can conduct electricity. Any material you can use copper, you can use aluminum, any material, it's a conductor. And here there is a needle, magnetic needle. This needle is a magnet. Now it's a magnet, it is indicating a direction. This needle is a small magnet. If electricity is passing through this circuit, what is going to happen? That we are going to observe here. Now you can see that electricity is passing through the circuit. When electricity is passing through this circuit, there will be small deflection. Reason? Why the magnetic needle is getting deflected because of this electricity? Reason is production of magnetic field. When electricity is passing through a conductor, there will be production of magnetic field. A current carrying conductor can produce magnetic field around it. If there is a current carrying conductor, there will be magnetic field. Now we are going to do one thing. We are going to change the direction of current. Now what is the direction of current? Current is starting from the positive end of the battery and it will end at negative end of the battery, right? So the direction of current at this conductor will be in downward direction, right? The electricity is starting from here and it will be in downward direction. When electricity is moving in downward direction, there will be deflection in the magnetic needle. You can see the deflection now. Now electricity is passing through this conductor, there is a deflection, right? It is deflecting clockwise. You can see that. Now we are going to do one thing. We are going to change the polarity of the battery. We are just reversing the battery. Now we reverse the battery. Now what is the direction of electricity? What is the direction of flow of current? The flow of current, if we are changing the polarity of the battery, the direction of flow of current will change. It will be opposite. Now it is a position of battery. Now the direction of current will be from positive to negative. The direction of current is always positive to negative. In the previous case, the deflection was in clockwise, right? What about this case? It will be in anti-clockwise. Now electricity is passing in upward direction. Electricity is passing in upward direction, there will be deflection, it will be in anti-clockwise. So when we are reversing the direction of current, the magnetic field, the direction of magnetic field will change. It will be opposite. Now we are going to find the shape of magnetic field produced around a conductor. So here you can see a conductor. There is a cardboard sheet. We are pouring some iron powder around it and we are passing electricity through this conductor. What we are doing here? We are pouring iron powder. If we are pouring iron powder, iron is a magnetic material. It will get attracted by magnet. And electricity is passing through this conductor. When electricity is passing through this conductor, there will be production of magnetic field. Now the current is flowing through the conductor. When electricity is flowing through this conductor, there will be production of magnetic field. And because of this magnetic field, the iron powder will get arranged in circular shape. We can conclude that the magnetic field around a conductor, it is in circular shape. Here you can see that it is in circular shape. A current carrying conductor will produce magnetic field. That magnetic field will be in circular shape. It is the shape of this magnetic field. It will be concentric circle like this. Magnetic field due to a current carrying conductor. A current carrying conductor can produce circular magnetic field around it. It's the conclusion of that experiment. A current carrying conductor will produce circular magnetic field. It's a very simple concept, right? It is a current carrying conductor and you can see the circular magnetic field. So we learned a lot of things in this session. First one was magnet. Magnet is having a magnetic field. The magnetic field is a region around the magnet in which the presence of magnet can be felt, right? Outside the magnetic field there is no magnetic force of attraction. Inside the magnetic field only there is a force of attraction. After that we learned about magnetic field line. Magnetic field line means these are the imaginary line which is going from North Pole and going to South Pole. After that we learned magnetic field intensity. Then we learned a current carrying conductor can produce magnetic field and this magnetic field will be in circular shape. Right hand thumb rule. This topic is very important and lot of applications are there. Using this thumb rule we can find the direction of magnetic field, direction of electric field. Magnetic field and electric field, these are vectors. These quantities are having direction. These are vectors. So we need to find the direction sometime. For that we are using this right hand thumb rule. You can hold your right hand like this. Okay, this is the thumb rule. Thumb rule. It is Facebook like, right? Just imagine you have a conductor. Through that conductor there is a current. Some current is flowing through the conductor. So we are going to find the direction of magnetic field around it. There will be production of magnetic field. We are going to find the direction of magnetic field using this thumb rule. We are assuming the thumb is indicating direction of current. Just imagine you are holding that conductor. You need to imagine that you are holding that conductor and the thumb is indicating direction of current. Thumb is indicating direction of current and encircling fingers will indicate direction of magnetic field. It is very simple though. If we are assuming that we are holding the conductor in your right hand, if thumb is indicating direction of current, then encircling fingers will indicate direction of magnetic field. This is a dislike button, right? Now the current is moving in downward direction. It is the direction of flow of current and encircling fingers will show the direction of magnetic field. It is a direction of magnetic field. Can we do it with an example? Right. Here we have a conductor. It is a direction of current flow. So there is a conductor and direction of current flow. It is in upward direction. We need to assume that, we need to imagine we are holding that conductor like this, right? So we are holding this conductor like this, right? You can see that. I am holding this conductor like this. Okay. Thumb is indicating direction of current. Perfect. Here in this conductor it is a direction of current and thumb is also indicating direction of current. What about encircling fingers? It is indicating direction of magnetic field. So what will be the direction of magnetic field? There is no doubt the magnetic field is in circular shape. So we are drawing the circular magnetic field, but we don't know the direction. For finding the direction we have this right hand thumb rule. Now the encircling fingers will indicate the direction of magnetic field. Now it is a direction of encircling fingers, right? So it is the direction of magnetic field. We can mark the direction of magnetic field. It is a direction of magnetic field. Now we are going to change the direction of current. Next one, we are considering the conductor. The direction of current is in downward direction. The current is flowing in downward direction. Thumb should be indicating the direction of current. So how we need to hold the conductor? We need to hold the conductor like this. Like this, right? Like this. Now, what will be the direction of current? Downward direction. Perfect. What is the direction of magnetic field? Like this. It is the direction of magnetic field. We are going to show that here. It is the direction of magnetic field. Circular magnetic field, but direction is like this. It is a direction. It is known as right hand thumb rule. Can we write the rule now? Right hand thumb rule. Imagine that you are holding a current carrying straight conductor in your right hand such that the thumb points towards the direction of current. The encircling fingers will show the direction of the field line of the magnetic field. It is known as right hand thumb rule.